شنجو شن الأمور. اليوم الفيديو هادي الموضوع اللي يحكي عليه كيف تخلي الكمبيوتر يفهم الكلمات. جهزوا هقولكم. خلونا نبدو. We're talking about understanding words today, and this is the second part of our natural language processing or NLP series. And words are some of the most important parts of language. All of us use words. You're listening to words right now. And so this is a fun topic. When we're talking about understanding words today, we're mostly going to be talking about a thing called word embeddings. And I just want to say that we're going to ignore large portions of amazing research because we're just skipping to the tip of the iceberg that is the most useful right now. So hopefully that's what you'll be seeing, and I hope you enjoy it. So let's start by this activity. I want you to think as you're watching this video to define the word game. What does it mean? What does the word game mean? What are some of the features involved with it? Think about that for like 5 seconds. And okay, so maybe you came up with something like it involves some competition, some rules, some entertainment, some skill or some chance. These are all things that you might say are related to the word game, right? But there's counterexamples. If you say a game has to have competition, well, what about like a crossword puzzle? You're not competing against somebody when you're playing a crossword puzzle game. What about rules? Well, if you're just kids running after a ball, there's not really rules to the running after the ball. It's just a game, you're playing it. Does a game have to have entertainment value? Well, a political game isn't really entertainment value. The Hunger Games, you could argue that there's suffering, skill, chance, everything that you could say about the word game that defines it. You could actually find counterexamples to something that is a game but doesn't have that kind of feature. So what the idea here is that the word game, or actually any word, is kind of slippery in its meaning. You know, it's not always, you can't always pin it down exactly, define it completely. In fact, most of the time you're trying to define it by other words anyways. And so it's a little bit difficult to exactly pin down the nature of a word. And so when we're thinking about how to get a computer to compute words, this is something we need to keep in mind. I just want to actually note also that, well, what if you are talking about another language, like the word alaba? I don't even know if I spelled it right, but that's all. It has a different semantic range in Arabic. It's a toy as well as a game, I think. And so different languages have different semantic ranges for the words that they use. And so that makes it even more challenging if you are going to be talking about the meanings of words across languages. I'm not going to talk about that much, but that's just a side note, that the meanings across languages are going to be different. So because it's difficult to pin down the meaning of a word, it's kind of slippery, we're going to define words, the meaning of words, by their context. And another thing from the 50s, this is this quote: "You shall know a word by the company it keeps." In other words, what sentences do you find it in? What phrases do you find it in? What documents do you find it in? And that will help you figure out what that word means. And when we do this, we're basically doing something we call distributional semantics in natural language processing. And we say distributional because the question is, how is it used or distributed in real contexts? You distribute some of the word game, it's distributed some in sports articles, some in political articles, some in different places. And so where is it distributed? And when we're doing distributional semantics in natural language processing, we're not doing knowledge-driven semantics. Now, knowledge-driven semantics, or meaning by what we know as humans, is the way that things were done previously, and we still do a lot of knowledge-driven stuff, but I'm focusing today on distributional methods. But that was like a symbolic approach. Basically, in the previous times when you had a knowledge-driven kind of paradigm, you would take a symbolic approach where you'd use a resource like a dictionary, and you'd say, hey, here's the dictionary entry or some other resource. Here's the entry for that thing. And then I need to human curate the resource, the dictionary or the whatever else it is that I'm going to use to get that knowledge. And I'm going to use that as my representation of meaning somehow. But it's a little bit hard to quantify that. And it's hard to quantify what the meaning of that one thing is, and it's hard to compare meanings between different things. So if you had two different words, like in Arabic you have yadam and yeshijo. I'm not sure I'm saying it right, but you have these words to sort of support and to encourage, and they're related to each other, but you wouldn't be able to get that just by looking at the letters that are involved with those words, right? They're semantically related, but it's hard to quantify how those things are similar to each other if you're looking at a dictionary or something like that. Okay, back to distributional semantics, what we're talking about today. So what we're talking about today will be data-driven or empirical meaning, meaning by looking at hundreds of documents of where a word shows up. And saying, well, what can we say given all of the contexts that we see it in about what it means? The other thing that we have with distributional semantics is that we're able to make quantitative calculations of something like similarity, solving the problem that I just showed above about trying to compare two different words. Okay, well, not exactly solving, but giving you a good approximation. So let's move into this distributional semantics kind of thing. We can call it word vectors. In other words, vectors, a sequence of numbers that actually represent a word. And so this is a quantitative embedding, a quantitative representation of words. I think that's really cool. This is one example. It's called explicit semantic analysis. I picked it because it's easy to learn from, I think. It's easy to get the idea of what we're doing here. So in the columns, this is a matrix here on the left side. This is a matrix. And in each of these columns, it's going to be a topic. Okay, an explicit concept in explicit semantic analysis is actually like a Wikipedia article on complications for a disease, for example, and risk factors for diseases, symptoms. This is just a Wikipedia page on what is transmission of diseases and treatment of diseases and stuff. Okay, and then in the rows, we're going to have words. Now I pulled all these are some of the most common words in the COVID-19 literature right now. And so in the rows, you're going to have words, or at least you're going to have numbers that represent words. And then the numbers that are actually there are going to represent how well was a particular thing expressed. So how often, how related is this word characterization, for example, to complications or risk factors or symptoms or transmission and treatment? And in this particular vector, what we're saying, okay, it's more related to symptoms. You're analyzing and characterizing symptoms. And the other thing you can see is that when you have a vector like this, when you have a sequence of numbers, some sequences of numbers actually look more similar to other sequences of numbers. And so the idea is that you want to have similar words have similar numeric signatures, similar vectors. Okay, so we're skipping lots of stuff like LSA, LDA, topic models. Explicit semantic analysis was actually a later thing, but I think it's just helpful for us to see that you can have vectors for a word that represents something. Okay, so now when we get into the deep learning era, the model that kind of got everybody's attention and became really, really popular was called word-to-vec. And these are really simple embeddings. And this is in the deep learning era, but there's even, you might even say that it's not necessarily a deep learning model. In word-to-vec, we're going to try to do the same thing again. We're going to try to get vectors with numbers that represent words. Okay, and so what we're going to do is we're going to take we're going to look for a specific word. So here we're looking for the word analysis. And say we have a text with the word analysis and a few other things in context. And so what you're going to try to do is predict the words that come around the word analysis in a text. So say you have a sentence that says kada 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 analysis kada kada kada, and you have like 2 words before it and 2 words after it. And what you're trying to do in this particular word-to-vec model, it's called the skipgram model, you are trying to take the word that you have and then predict what are the words that are going to be nearby the word analysis. Okay, and the way that we're going to make this prediction, well, let me just back up a little bit. I forgot to talk about this. So the representation for the word analysis is what we call a one-hot vector. In other words, there's a 1 here for the word analysis, and everywhere else for this vector, which is going to be as long as the whole dictionary. It goes from A to Z. There's a 0 everywhere else except for on the word analysis, or whichever word that you're looking at in focus at any particular moment. Okay, so we want to predict the context words, and those context words are also going to be represented similarly. Okay, so how do we do that? Well, we want to get from this large vector that's as long as a dictionary, squeeze it down into a smaller vector in between by means of some linear algebra operations. We're going to use matrix operations. So matrix times vector equals another matrix, and then this matrix times this vector is going to output these different matrices. And so basically what we're going to do is learn these matrices based on lots and lots and lots of examples of these of the input word analysis with all of its contexts, and then you put in another document with the word analysis and all of its contexts, and you just put in example after example of all those things, and then you're putting in examples of other words as well, not just the word analysis. You go on to antibody and you do that. Practically speaking, what you're normally doing is iterating through a document instead of doing this analysis thing. So when you're trying to learn these matrix weights, the learning objective, you can actually transform the way that this thing looks rather than directly having it represented as we're showing graphically. People do things like negative sampling or noise contrastive estimation, which I'll show you later. But the idea is that that you're basically trying to predict the context words here in Word2Vec. Now, just to point out, we were talking about word vectors in the previous slide, and where are our word vectors now? Well, it's in the columns here in W, because in this weight matrix, what you're doing is you're trying to convert something from the vocabulary size here in XT into something smaller, usually 200 or 300, dimension of 200 or 300, instead of 10,000, 100,000, a million different words in a dictionary. You squeeze it down into 200 or 300 elements in a vector. And so basically for each one of the say 1 million words in your vocabulary, you're going to have a 200 or 300 element vector corresponding to a column in this matrix. So that's where your word vectors are. Now, Word2Vec is really popular. It's very fast. It's effective in a lot of ways. It does a lot of cool things, but it's also superseded by lots of other cool models. It's been extended. There's been a lot of other things, and we'll talk about that. And the result is basically that vectors are basically behaving as if they understand people. And so what I'm going to do is pull up a terminal here, and let's see. And let me just show you. I've loaded some pre-trained vectors. So these are fast text vectors. This is a different model. besides Word2Vec, but this is fast text vectors, and I'm loading it in here. This is a Python script that just loads up this vector file that I downloaded from fasttext.cc, and you can see what it does pretty simply. And let's just run. Oh, let's see. Let's just run this. This is not present. Maybe I need to unzip it. Let's see what's going on here. Yeah, I need to unzip this. Might take a little time. And, bummer. Zip period, not an archive. Let's see. Oh, I did not get this ready. I'm going to cut this part out, and I'll come back. Alright, so I've gotten this to run successfully by loading up this vector file here. Wikinews. So this is a 300-dimensional vector with a 1 million size vocabulary, and I've set it up so that I can look at the vector for any given word. So the words that became really important to the natural language processing community were these ones. The vector for king, okay, it's just a bunch of numbers, right? The vector for queen, if you just look at these individually, you can't really tell anything about them. But the thing that you can do here is you can actually do arithmetic. You can say the vector for the key. Okay, so let me first say you can compare two different vectors by giving their cosine similarity. This is just the dot product over the product of the magnitudes of the two vectors. So you have the vector for king, and let's say the vector for ruler or something like that. And those are related to each other, so they have a reasonably high. Whereas if you had something like king and what's something completely unrelated like eraser or something, okay, not very high, right? It's definitely lower. Okay, so now the interesting thing is that you can actually do arithmetic here. So because the vector for king is just a vector, you can actually say, hey, I'm going to subtract the vector for man and add the vector for woman. And that'll give you another vector. And the idea is if you're subtracting the vector for man and adding the vector for woman, then it's like an analogy. You're basically creating word analogies. And if you do a search, I don't have it implemented here, but if you do a search for the closest vector to king minus man plus woman, then you would get something like queen. And when it was shown that this was possible in using word vectors, and that a really simple algorithm basically was able to do this kind of stuff, natural language processing people kind of lost their minds and were like, oh my goodness, this is amazing. And people started doing word embeddings from 2013 to like 2015. There's like everybody was doing word embeddings of different kinds. So anyways, so all that's to say basically that when these oh, sorry, let me just get to the right slide there. All that is to say that vectors behave as if they understand when you're comparing meanings of different words. It's pretty neat. Now, I've shown you these word embeddings. These were pre-trained word embeddings, and so the question might be like, how do you build word embeddings? How do you use word embeddings? Well, there are a lot of different models of word embeddings, and so there are different ways to use it. Word2Vec, Glove, Fast Text, Elmo. Word2Vec was the simple one that I showed you with the skipgram model, but Glove has a different way to reduce the dimensionality. Fast Text has a subword model. Usually, most people talk about the fast text that has a subword model. In other words, it will look at units smaller than the whole word, so you can have a meaning of just a part of a word. And Elmo is looking at word embeddings in context. You get a word vector, and so the word vector for the word bank when you're in a financial situation, and the word vector for the word bank when you're talking about rivers and things like that. These are different. It's going to give you a different vector for the word bank. Um, Word embeddings can also be built just by when you are creating a neural network and you input text, you basically have to start with an embedding layer. Either that or you start with the one-hot vectors that we were talking about, but those are really not very effective because there are so many, the vocabulary is so large, and so the vector is very sparse. It's not very useful. So with any normal neural network, you can actually train word embeddings from scratch. You might not actually pull them out and compare them similarity wise and stuff like that, but you can train embeddings of words on any task that you do with a deep learning network um, with input of text. There are actually a lot of pre-trained models available so that you don't actually have to build your own word embeddings in terms of coding the algorithm, but you can co-train. You can start from pre-trained models that people have released on the web. I think all of these common models have pre-trained models available, and then usually you can add on some of your own data on top of that. I'll say that building word embeddings, I just want to note that it's not perfect for Arabic and for other morphology-rich languages. In other words, languages that do a lot of the grammar just inside of a word. You know, like you know, ati huna fi or something like that. You know, like ati huna. Like there's a lot of different things happening in that one verb. Um, so, anyways, this is um, there's a lot of work being done in a lot of languages, but I'd say specific work that is precise and really helpful for Arabic and for dialects of Arabic is still needs a lot of work. I've worked on Amharic, which is another morphology-rich language with even fewer resources, and yeah, needs definitely needs a lot of work. Um, so I want to just point to a few resources on embeddings that you can look at. For example, if you were to want to build simple vectors like the word-to-vec model that I showed you, the skipgram model, using, say you wanted to build that using Keras on COVID-19 data. I'm not going to walk through all of it, but let's see, let's just go to the main Kaggle page here. Remember this COVID-19 research data set challenge, COVID-19 open research data set challenge, where you can look at tasks and try to answer questions like what is transmission, incubation, environmental instability, whatever else. The neat thing about tasks that are organized on this website, kaggle.com, is that, well, they're usually well put together, and they have the data and the evaluation there for you. And so what you can do is you can click on new notebook, and you can create a new environment, and it will give you basically what we like a Jupyter notebook, Jupyter. If you're not familiar with it, you can run Python in your notebook at the same time as writing texts using the Markdown formatting. Um, and so it's a neat way to do interactive data analysis. So anyways, the thing to point out here is that say you want to do some work on COVID-19 and NLP, well, you can look into the data here. It's just provided all right here for you, and you can see how this is like one of the these are some of the articles in JSON format that are part of the data set. So here's molecular advances in the cell biology of SARS-CoV, not CoV-2, I guess. But then here's the body text, and you have the full text of the articles along with a bunch of other metadata. Um, and I played around with this, so I have some code that um, pulls out the data and then gets it ready for for word embeddings and that kind of thing. And the other thing to point out, I guess it's taking a while to load here right now, but in this Python environment, in the Jupyter environment here, notebook, it actually gives you the one that's here on Kaggle.com. Has all of the scientific and technical libraries loaded. So I recommend Keras, Keras, for deep learning, and it's already preloaded and stuff like that. You can directly import it and any other libraries, NumPy, SciPy, Matplotlib, lots of those, anything having to do with data, because that's what Kaggle is made for. So check out Kaggle. Here is a really good tutorial on using using Keras to implement the skipgram word2vec model, and um, I've done most of this one, and I think it's pretty neat. It shows you how some of the model that I was showing you earlier in the slides, you modify it a little bit in order to for the actual implementation. And so that's what I was talking about. The objective being noise contrastive estimation. Let me see. Here we go. All right, there's negative sampling, or yeah, actually, I think they use negative sampling instead. Okay. Um, and so yeah, here, uh, yeah. So the architecture is a little bit different. The negative sampling architecture is a little bit different than straight skipgram, but it's trying to do basically the same thing. Here in the negative sampling architecture, instead of having the target word, like we were looking at analysis, instead of having the target word and then predicting over here the context words, here you're going to say you're going to have a pair of target word and context word, and then you say, is it really in the context or not? Yes or no. And then you put in random other words from the dictionary instead of the context word for negative samples of this thing. So that's why it's called the negative sampling architecture. Sorry, I'll make this a little bit bigger. Where did it go? Yeah. Oh, okay, it's not that much bigger, but anyways, you get the idea. You're putting a target word and a context word together and saying yes or no, is it in the same context or not? Okay. But it does go through all of the actual coding of how to put something together. I'll just say here that the layers in Keras are fairly easy to put together. This is with this particular negative sampling architecture, you have to use these input and embedding kinds of things. But they're for simpler architectures, actually not necessarily simpler, but different architectures, you can use even easier uh, layers to do things, to do different functions and stuff like that the with the data that you're passing through. So those are some resources for getting started on doing embeddings in, and yeah, you can implementing one of them helps you get a leg in on other ones, and especially getting into Keras, I think will allow you to get further into embeddings or into other types of models. So anyhow, the conclusion is that words are slippery and it's hard to pin down an exact meaning, but we, when we're trying to understand words with computers, we look at tons and tons of data and try to use the data and the contexts in around words to understand what they mean. So we talked about trying to build word embeddings. You can sort of take existing pre-trained models, like the one that we used with fax text. Also Elmo, or any of the pre-trained, any of the common models have pre-trained models. Then you can check out other deep learning models in Keras. You can check out the COVID-19 data and the environments that's set up for you in Kaggle. And lastly, invite you to like our Libya AI page on Facebook, and stay tuned for the next video. All right. Thanks for your time. God bless.